Hi, and welcome to Electric Fields Lesson 2A. Today we're going to be really honing in on field lines, just making sure we've got that absolutely rock solid. Because this is the kind of question which can be at the start of sort of a 20-mark nonsense question. If you get this bit wrong, everything else can go to pot. So make sure you can do this. So, what is a field line? Just pause this video, just think to yourself, do I know the definition of what an electric field line is? An electric field line represents the direction of the force on a positive test charge. So in other words, if we've got a tiny bit of positive charge at that point, what direction would it move in? So we start with what are called parallel plates. So this is simply you've just got two metal plates, you've taken the electrons off this one, you put it onto this one. What's the electric field going to be in between these plates? We use these plates a lot because they're the only real way to get a nice, consistent electric field. Whenever we're going around single charges, as we'll see in a moment, it all goes a bit messy, but between two plates we get a nice, simple one. So it's positive charge, it's going to move away from the positive towards the negative, and we're going to get it like this. Next question is, how would we represent a stronger field though? If we were to up the voltage, rip more electrons off this one, whack them onto this, how we do that? Exactly the same as gravitational fields. It's going to be how close together the lines are, the density of the lines. So we put more lines in, that now represents a much stronger field, which will have stronger effects. So what are the field lines going to be like around a single floating positive charge, like one proton floating by itself in space? What are the field lines going to be? We just need to think for a moment carefully about the direction of the field lines. It's positive charge, so we're going to be going away from it. So what you're going to end up is just something that looks like this. Sort of the opposite of the field lines we've been drawing around a planet. Equally spaced all the way around, all moving away from it. So think about it, if you're a positive charge, wherever you are close to this, you're just going to be pushed straight away. Now I've got something a little bit more interesting, which is two negative charges fairly close to each other. I'm just going to move this one slightly further away. So what's going to happen here? Well, if you're a positive charge over here, you're just going to be pulled into it. Same here, same here, same here, etc., etc. However, an interesting thing is going to happen in the middle. Because if you're a positive charge here, you're going to be pulled towards this one. You're going to sort of slope in like that. Same here. If you're a positive charge here, you're going to be pulled in like that, pulled in like that, which gives us a region of no lines here in the centre. Is that okay? Yes, it is, because if you're here, positive charge, you're going to be pulled towards this one and pulled towards this one equally, so overall there'll be no force on you. So overall there'll be no force, so that makes perfect sense. Now, because we've got both plus and negative charges, there is actually another type of field line drawing we could draw, which is if we change one of these to positive, so we had a positive and a negative, what would the field lines look between those? I want you to actually draw it, have a go, I'll tell you in the next lesson.